Yeah. Yeah, so far we were discussing about horizontal scaling, distributing the data, partitioning everything. Now let's come back a bit towards the client side. So now let's assume we have horizontal scaling, we have many backend servers, and of all of incoming requests from the clients, now we need to send them to the servers. So even if there is only single backend server, we cannot just expose our entire internal systems to the public. So we need to ensure the security. Uh, yeah, I will share the link after the session. So we need to ensure the security. That's like we are protecting our own infrastructure from the public and misuse or from the attacks, and ensuring the proper identify users are using the system in an authorized manner. So for that, there are multiple options. One is the reverse proxy, other one is the load balancer. So we will go through what is a reverse proxy, what are the pros and cons of this one, and then what is a load balancer and why we go for the load balancer over the reverse proxy, when to go for the reverse proxy and when to go for the load balancer. So this is what we discussed today. Now, before starting on what is a reverse proxy, first I will tell you why we call it a reverse proxy. So usually in our internal organizations, we say VPNs, firewalls, and whatever we are using, the public system we are using, the internet. For example, if you are trying to access the Facebook from your organization VPN or internet, these are all protected, monitored. How it is done using the proxies. So I will just try a diagram. So for example, employee 1, employee 2, so on, and there is a Facebook. And whenever the requests from the organizations are going outside, these are all first going to the proxy, and from the proxy, these are going to the external world. So this is our internal infrastructure. So here the proxy is to protect the identity and IP addresses of our internal infrastructure from the public. So here proxy is from internal to external. In between internal to external, it is sitting, and it is monitoring all the connections going from the internal to the outside, and then ensuring the security, telemetry, and a block list in case, for example, an organization doesn't allow Facebook accessing to Facebook from inside the organization. Those block list and firewall, everything is in this proxy. So this is simply a proxy. Now coming to the reverse proxy, this is other way around. If you see, it is from the external to the internal. So the clients which are external are trying to access our internal infrastructure. So that's the reason we call it reverse proxy. So this is doing the opposite, other side. So it is trying to protect our internal infrastructure from the incoming requests. That's the reason that name comes as a reverse proxy. Now we'll discuss why do we need a reverse proxy. So even if you have a single backend server, for example, you're starting your own startup and you have deployed one backend server and serving the requests. Perhaps the single one is sufficient enough for serving your incoming requests, but then you need to ensure the security and rate limiting. So these are all the features provided by the reverse proxy. First thing is security. Hides information about our backend servers. You don't need to give your public IP to your backend server directly to the external world. Doing so can compromise on the security. So you're trying to hide this information of the internal IPs of your backend servers directly to the public. That is one thing. Second thing is rate limiting. So if the IP address of your systems are directly exposed and all incoming requests are directly hitting your backend system, that's when attacks can happen, like DDoS attacks, where there are a huge number of incoming requests trying to overload your system, take it down. So that's the reason you wanted to ensure the rate limit by ensuring that there are only this number of requests can come from this particular IP or user per second. So this kind of rate limiting can be done using the reverse proxy because it sits in between the clients and the backend systems. So in between, sitting like in between both of these and acting, looking into the each and every incoming request and doing this security rate limiting jobs. The other one is the authentication to ensure that only authorized users are hitting the system and using the services. And the other one is the SL termination. In case of SSL, you're using the certificates and you need to have this trusted root certificates to decrypt incoming requests. In the all incoming requests, for example, HTTPS is having SSL. Those are encrypted and these need to be decrypted. There are multiple reasons why you don't want to do this everywhere in your backend systems. You can do, but there are problems, and not doing so, there are some advantages. First thing is, for decrypting a incoming request, SSL request, you need to have a trusted root certificates. So if you're keeping the SSL termination, that means you're terminating the request from SSL at the reverse gateway, reverse proxy. Then you don't need to have this trusted root certificates installed on all your backend servers. For example, if you have thousands of backend servers, you don't need to have the certificates in all of them. Second thing, this encryption and decryption, these are very costly. These are very CPU intensive. So and to make them faster, sometimes we deploy special kind of hardware to take this, do this work at the hardware level, or even dedicated servers to do this in the software. So instead of doing this in every backend server, we can isolate this work into our internal reverse proxy.
Just a second.
So,
we have a question from Omar. Omar, did you want to ask your question before proceeding?
Yeah.
Yeah.
Quick question.
Yeah.
Talking about SSL termination for reverse proxy. Suppose I'm in the company and I get a WhatsApp. I'm on company Wi-Fi and sitting inside the office, and they have a reverse proxy, and I get a WhatsApp message. Does it decrypt it at the internal? Like, can the admins view my encrypted messages from Facebook and WhatsApp? How does that work? Thank you.
I don't think this reverse proxy is taking your personal WhatsApp messages, because this reverse proxy is for the incoming request for your APIs that your internal infrastructure is serving. For example, if you're working for google.com, let's assume. So the google.com reverse proxy is only taking the requests which are for the APIs related to google.com. For example, get google.com and so-and-so page, post google.com so-and-so page. These are dedicated servers for dedicated purpose, not for the WhatsApp. WhatsApp is not really going through the your company's reverse proxy at all. So if I show you here one example, let's say I'm saying get google.com and so-and-so page number 1. Let's assume this request is hitting your. This request is going to this. It is coming from client and which is going to the reverse proxy. So this is routed. The IP address, when you say ping.google.com, the IP address you get, that is a public IP address for your company's organization. And the requests are coming for that IP address. And those IP address requests are going to the reverse proxy or the load balancer. But whereas the requests which are coming to your WebSocket, those are not going to google.com IP address. So your WhatsApp or your personal, anything which are not related to the APIs of your company, your organization, not going to the company's infrastructure at all. They're probably going through the VPNs. They're probably going to VPNs and firewalls, I suspect, but probably they're going to the VPN which is covering entire Wi-Fi. But ideally, organizations, I don't want to get into this, but just a quick statement. Organizations don't decrypt your personal messages. Even if they do so, they can get huge fines if
Yeah.
those are discovered. So they don't get into those kind of business at all.
So my question was, thank you very much for your answer, but like it is possible, like if I want to implement this for my kids at home and I implement the reverse proxy, can I decrypt these messages just to maybe like protect the young ones? Is it possible to decrypt these messages on a higher level before it reaches the end user? That's my question. Thank you.
So in that case, you need to do something at the router level, not this reverse proxy is for the organizations. You need to do something at the router level. If you are having admin access, you need to do that at your router level.
So, so the reverse proxy is basically like she said, the job of the reverse proxy is to protect the internal organization, right? So your kids in this stage, it's your kids, and what you want to do is so when you are offloading, so the external to internal comes via the SSL is still on, but from the external, like from the reverse proxy to all the internal systems, you might want to do an SSL termination because it is secure. You've ensured that it is secure, and the cost of, like Shailaja mentioned, the cost of this SSL, if you didn't terminate, it's quite costly, and compute costs. So what you want to do is terminate the SSL on the reverse proxy, and then you will use HTTP or whatever protocols internally when you know that your internal services are secure, the authentication and authorization is spot on. So that is the scope of the reverse proxy.
So we are mixing it. There are two different things altogether here. The reverse proxy is for the targeted IP addresses and targeted APIs. Whereas what you're doing at your router level, those are for any incoming request, not for any particular IP, not for any particular app, not for any particular API. So reverse proxy is not for that, unless you know, okay, this is the IP range I'm planning to cover, and this is the APIs I need to cover. That is the one thing. Second thing is, even for the SSL termination, you need to know what is the SSL algorithm used, what is the logic to decrypt them. For the WhatsApp, they are doing their own things, so you don't have access to that. Only WhatsApp client can decrypt it. Only WhatsApp server can decrypt it. No one in the middle can intercept them. So all that you can do at your router level is install some app to intercept every incoming request and do some action on them, but not particularly for the WhatsApp. Even probably there are apps to do that, but these are totally different domains. So reverse proxy is for the organizations for their incoming requests, not for everyone. Even if you are working at the Facebook Meta, only reverse proxy is only taking care of their incoming requests, not for other services or not other apps. Actually, can you take questions after covering the reverse proxy section? Because otherwise, there will be questions which are not covered, yet to be covered. And also, it will be like, I receive some comments like, it's like one-on-one sessions for some certain set of people. So that's the reason I want to first cover one section. And then I will take questions from everyone, not focusing on any one person. And then we'll go to the next section. Is that okay?
Yeah, that sounds good, Shailaja. Thank you.
Yeah. So second, the other thing is the compression. So even compression, decompression are very CPU intensive jobs. So if you, for example, if you're serving object storage service, in that case, all the incoming data is usually comes in the compressed format. Sometimes normal incoming requests also can be compressed, though usually it's costlier operations, but sorry. So if your request is hopping through many backend servers, instead of doing this compression, decompression at every stage, you can have one common place. There's a reverse proxy, and there you can do the compression you can do the decompression of the incoming request and send that decompressed data to the backend server. So backend servers don't have to do anything else, directly access the data which is incoming. Similarly, when the response is going back, when the request is processed and you're sending some data chunk back to the client saying that, okay, here is your data. That data usually we send it compressed format to reduce the amount of the data amount of bytes we send out, and also to optimize the network bandwidth. So this decompression also, the backend servers, instead of doing it on their own in the backend, this can be handled in the reverse proxy. It's like in your building, you're having a gate, and at the gate, the security person is doing all identity checks for every incoming person, and then making the general records of who are all coming and doing some specific actions as per set by your building rules. So the reverse proxy is like that. So it's like a gate for your internal organization. And then after the compression, decompression, and also caching. So there are some requests for that. The response probably is the same, even though multiple users send the same request. For example, if I'm asking, get me google.com latest news, and in that case this is the same answer for any user asking that. So in that case, the response, once the first time when the reverse proxy gets a request, it probably send the request to the backend servers and process the request and got the response back and cache it. When it caches the response, when the same request comes again, even from the same user or from the different user, the reverse proxy can directly serve the request without going back to the backends. So here there can be a caching layer here. Here that there can be caching layer. So the first time when the request comes, it sends the request to the backend server, gets the response, does cache the request response, and serves the request back to the client. And for this cache, usually a TTL is associated. TTL is the for how much time that cache need to be alive. Let's say I keep it like a 1 minute. So that means within 1 minute, whatever the request coming for the same request can be directly served from the cache in the reverse proxy without hitting the backend servers. So that is another advantage of the caching. And then most of the times the static content is very good to be served using the cache. For example, the HTML pages, so HTTP pages, those pages which are pretty much having at least 80% of the page as static content. This content can be cached in the reverse proxy on the fly. If needed, any little dynamic data can be inserted into it and sent it back to the users. So we are trying to avoid most of the duplicate work by using this centralized reverse proxy as a way of mechanism to cache the information. Now we see, obviously we get a question. So now reverse proxy is sitting as a centralized place to do all the incoming requests or process all the incoming requests and the response, etc. So obviously the problem is single point of failure. If the reverse proxy is going down, that means all the incoming requests will not be processed by our system. So usually to avoid the system, we usually do the redundancy by using either active passive or active replicas of the reverse proxy. So if this reverse proxy is dying by any chance, we ensure that there is another reverse proxy. It can be, we actually already discussed active passive and active modes in the previous sessions. So in that way, those are configured. That way, even if one is dying, the other one immediately takes the request and starts serving the request. So we need to ensure these are highly available. So this is in a high level, what is a reverse proxy. Now, if you see how reverse proxy sends the request to the backend server, usually you can do this using the rules, because if there is only one backend system, it's pretty obvious. All the incoming requests are going to the same backend server. If there are more than one backend server, you need to define the rules how to pass which request to which backend server. So for example, you can say that if the request is coming for this your domain name, send the request to API server. If the request is coming to another domain name, send the request to another front-end server. So this way, this is based on rules. If you see, this is not a load balancer reverse proxy. Now we will come to the other solutions which are nowadays we are having both reverse proxy and load balancer both together in the same system. But right now, just differentiate what is reverse proxy from a load balancer. A typical only reverse proxy does the redirection of the request based on the rules that we define, not like a load balancing algorithms or in other forms. So yeah, once now I will take questions on this one. Once that's done, we'll go back to the load balancer.
So one of the use cases my organization uses reverse proxy, we use YARP, is to apply transforms on the incoming request and the outgoing response, like updating the headers and updating the body if required, if need be. So we apply transformations. So I wanted to, I wanted to highlight that point, and if you could speak on it, that will be great, Shailaja.
Oh, sorry. Is there a question? I didn't get you.
Yeah, so I was asking you to speak a little more on applying transforms for the incoming requests and outgoing responses, like updating headers. I think you briefly touched it in terms of caching, like, injecting dynamic data. So I wanted a little more explanation of, like, one of the good things about reverse proxy is you can actually apply transforms, and speak from your experience on this.
Oh, coming to experience, I'm not a networking person, so I really didn't dig into the reverse proxy code, but there are open source codes like HA proxy and Nginx. If you want to have a look at the code, those are open source. I didn't really, to be honest, I'm mostly in the storage person. No, I didn't really hands-on into the
Okay.
reverse proxy code.
Yeah.
But
Yeah.
at high level, how it works, that I can just quickly cover in my theoretical knowledge. The actual practicals may be similar or could be different. So, for example, if you're having a HTML page, and in this case, let's say weather, or let's say weather. So usually if I want to get weather for London, you usually see the London weather information, and somewhere here probably your some personalized information like welcome Shailaja, or how are you feeling Shailaja. Simply just take an example. Okay, so in this case, if you see the rest of the pages, most of the HTML content is static. Some page is dynamically retrieved from the weather server, saying that, okay, go get me weather for the London today. Okay, I get that information. I inject this information into this HTML page where I need to have the weather information for the London, and maybe a bit of the personal information based on the user. Let's say, okay, I got a username Shailaja, so I say that welcome Shailaja, or how are you feeling Shailaja. So this reverse proxy, I'm not sure are they really doing that, but usually the higher end load balancers usually do that. They do have the static content either themselves within reverse proxy, or it could be their own database depending on the content size, and they take the static information from here, and then they insert the dynamic information which they get from the backend server and send the response back to the end users. So this static content, even in case of the London weather, probably at least 100 people are asking what is the weather today in London, like in next 1 hour. So this London weather can also be cached. So the reverse proxy probably can be attached to a typical key value store and having some information like London and the cached weather information. So using this mix of static and the dynamic content, it can generate a page here and send it back to the end user. So because every request is going through this reverse proxy, every incoming request is going through this one. This is a centralized place, so this is a good place to do this kind of optimizations. Did I cover? Do you have any questions? Are there more questions?
No, that's it from me. Thank you. I will just put in what, just give a pointer for y'all to the rest of the people who are interested. Any questions from anyone else? Thank you, Shalaja. That was really useful. And I really love the fact that you distinctly, the distinction between what's a proxy and what's a reverse proxy. I think, I mean, so far, yours is the best explanation I've come across. So beautifully done as well. Thank you. Anybody else with any questions? Okay, Irene.
Hi there. I might have misheard, but Shalim, when you were speaking there, did you say that you thought the load balancer loads the dynamic data and not the reverse proxy?
So reverse proxy can also do that depending on, so nowadays it's very difficult to differentiate between these because we are having many open source services as well doing all these jobs, including load balancing, without load balancing as well. But a typical reverse proxy can do any centralized job except load balancing. The load balancing is usually the distributing the incoming requests to the multiple servers in the backend. We will come to that. Load balancer, we will come to that in the next section, how it is doing, how it is slightly different from the reverse proxy. But except the distributing of data to multiple servers for horizontal scaling, anything which is common in a centralized system, that kind of work can be done in the reverse proxy.
Okay, thank you. Thanks.
So yeah, now before going to the next section regarding the Omar's question in the WhatsApp thing. So I'm definitely I'm not a network person, but in the reverse proxy, you need to tell the reverse proxy which IP range you are covering, which APIs you are covering. So whereas the incoming requests to the from the WhatsApp, those are not in your organization IP ranges, not the APIs that your organization is taking care of. So those don't go to your reverse proxy. Those go to Meta's reverse proxy or Meta's load balancers because those are the IP ranges they do cover. Now, if you want to do something similar in your at your home, because reverse proxy you need to tell the IP ranges and APIs, etc. And also reverse proxy is very complicated to set up because you're having control at the router level. If you're having admin access, there you are having access to every incoming request to your router. It may not be WhatsApp, to any other app, any kind of request it is. There you can install some of the software to filter based on the incoming request or the kind of request. But the reverse proxy is definitely overkill for that one, because reverse proxy is very complicated, higher end system for supporting organizations. And also you need to be able to configure the IP ranges and your APIs there. And also regarding the decryption and encryption, when you are trying to decrypt, you need to have access to the key, and you need to have access to the decryption algorithm to use. If it is something WhatsApp is doing, I think only WhatsApp server and client can understand that. It's very difficult to intercept in between and do anything with that. That's my understanding. Did I answer your question, Omar?
Yes, thank you very much. I guess I was looking at it from like more of a security point of view, and reverse proxy is more of like you said, routing requests to the required server more than like routing more than a security issue. For a security issue like files and things or like content, I think a firewall would be more appropriate here.
Absolutely.
Yeah, so it's totally a bit off the topic, but when you are trying to decrypt, when SSL request, incoming TLS request, you need to have access to the certificate and the key and the trusted root certificate value. So all these, I think, are available only to the WhatsApp client to be able to do that. And anyone trying to intercept in between, if you look into the asymptotic cryptography, it explains why anyone in between cannot intercept and decrypt a SSL request. So coming to the load balancers, yeah, now we'll explain how these are differing from the reverse proxy. So load balancers, you can say that these are more powerful than the reverse proxy. These are for higher end systems where you're having when you're trying to achieve the horizontal scaling and when you're having multiple backend servers. In that case, it is a simple reverse proxy. While it is ensuring the security, SSL termination, caching, routing, everything, it doesn't do one job that we need. That is distributing the request to one of the backend servers. So, for example, if I have server 1, server 2, server 3, and all of these are, let's assume, doing the same job. Like, for example, I have photo service, and the incoming request, I'm going and fetching the corresponding photo from the backend and retrieving and resending it back to the end user. How we usually design the backend, as we discussed in the previous sessions, we do have databases for the persistent information. Persistence data goes to the persistence layer, and we have services which can access any of the persistent layer and get the data. These are usually stateless usually. So that means any incoming requests can be taken by any one of the stateless server, the stateless service can say, and this stateless service retrieves information from the stateful services like databases, and gets the data and sends it back to the load balancer and eventually to the client. Now, why we need a load balancer here? Now I have 3 services running, both 3 of them are doing the same thing, photo service, going and retrieving the data. Now, we already discussed why we need multiple instances of the services for highly scalable and horizontal scalable systems. Now, load balancer has to decide to which service which instance of the service I need to send a request to. So based on some factors, load balancer decides where to send the request. For example, if you take a simple based on the amount of load on a particular server, if, for example, this server is busy, let's assume 10% of this server is busy, let's say 20% of this server is busy, and 30% is busy. In that case, load balancer has to go and pick the least busy one, that is a server 1. So it sends a request to the server 1, which processes the incoming request. At the same time, if I get another request, then because it is serving another request which we just now sent it to it, let's assume this one is a bit busy, more busy, let's say 20%. In this case, this one is 30% busy, this one is 30% busy, then the load balancer sends the next coming request to the server 2. So based on some logic, there are many different algorithms. We will go through them in a short while. Based on different algorithms and particular algorithm that you configure load balancer to do, load balancer choose which server the request has to go to, and that server will pick the request and serves it. So this is the additional functionality that load balancer does and reverse proxy doesn't. So, but in nowadays, it's a bit difficult to just differentiate which service is a load balancer, which is a reverse proxy, because many of the open source services are also doing both the jobs. They are doing both the reverse proxy and load balancer. Those are providing options to configure just as a reverse proxy if needed, or also can be configured as a load balancer if needed. But ideally, in a theoretical way, why load balancer is different from reverse proxy is this logic of distributing requests to multiple instances of the backend system. This logic doesn't exist in the reverse proxy in ideal situation. So if you see in the load balancer, the main important thing is distributing the incoming request to the servers or databases and sending the response to the client. So we'll come back to the response, whether synchronous, asynchronous ways. We will discuss them in a short while, how the response will be handled in different situations. And then there are hardware mechanisms to do the load balancing very faster way, in a very quick way for higher end systems. Or else there are open source free versions as well, only the software, which are good enough for the moderate amount of moderate size systems as well. And then the main advantages of the load balancer. First, it detects which servers are down. So we discussed the high availability. In case of high availability, if one of the server is down, let's assume if one server went down in this case, okay, sorry, which is here. If this one went down, the incoming request shouldn't go to this server because it's already gone down. So load balancer detects that and it doesn't send the request, incoming request to server 1. Instead, it sends those requests to server 2 or server 3. But how do load balancer detect that? So usually the servers do have a health service running, like a heartbeat. So every few milliseconds, they keep sending just a you can say test packet saying that I'm alive. This keeps sending messages to the load balancer saying that I'm alive, I'm alive. Now, when the server is down, it is unable to send the I'm alive packets to the load balancer. And load balancer doesn't immediately say that, okay, this server is down. It waits for a couple of minutes as configured by threshold, maybe for example, 1 minute. And after waiting for 1 minute, if there is no I am alive pocket, that's when load balance declares itself that, okay, server in its metadata, it declares that server 1 is down. So no more incoming request to server 1. And then it sends a request to other alive systems. Similarly, not only I'm alive messages, also every server periodically keeps sending how busy it is, how much CPU it is using right now, how much memory it is using, so and so. So based on those metrics, load balancer will be able to determine how busy each server is. It assigns a weight information for each of the server, and then when there is incoming request, based on the weight information and based on the configured algorithms, it will send the request to corresponding server. Okay, here. Yeah. So first thing is request ongoing to unhealthy servers. This is avoided using the health metrics, and then prevents overloading the servers. As we discussed, there are multiple algorithms. We'll come to them here a little while. And this sends a request to least overloaded servers instead of overloading already busy servers. And the other option is avoiding single point of failure. See, here I need to differentiate. There are two things. Load balancer is avoiding the single point of failure in the backend by allowing high availability. If there is a load balancer, that's only when you can ensure backend is having high availability, because when one backend server is down, another backend server is taking the request, load balancer can detect it and send the request to it accordingly. Without load balancer, even though if we are having high availability systems in the backend, the actual client will not be able to understand that, and the client will not be able to know to which backend server the request need to go. So the load balancer is empowering the high availability of the backend servers. But the load balancer itself can become a single point of failure if it is not configured properly, because it's like a Superman. It's sitting here doing everything for and to empower the backend systems. It's saying it is giving the complete freedom to the backend systems to fail and pass the request to other servers, so and so. So load balancer is doing everything needed as a Superman. But when the load balancer itself is down, that's when we need to ensure the high availability of the load balancer. So there are two different points here, if you see, so don't get confused. The advantages of the load balancer is it's avoiding single point of failure of the backend system. And in the cons, you will see again, in the cons, that itself, load balancer itself can become a single point of failure. And then we come to the SSL termination. Yes, it does, load balancer is more higher than reverse proxy, so it can do all the jobs that reverse proxy can also do. In addition, it can do additional jobs as well, because load balancer is having is a bit more powerful. It can do the session persistence. It can have a database attached to it. And when there is an incoming request, it can establish a session information for that user, write it into the database or in its key value store. When there is another request from the same client, it can send the same request to the same server again. So that is a session, that is that's we call sticky sessions or session persistence. For example, the first time when the client was sending the request, load balancer takes what is your login information, what is your role, login, which IP are you sending the request from, which location are you sending the request from. All that information it maintains in the metadata. And then let's assume this information is sent to the server 2. Let's assume that there is a client one sending the request again. In that case, the load balancer doesn't has to take all that information from the client one again. So if you see, when you go to a web page, first time it will ask you to log in. And when you log in, even if you visit the same page again after a couple of days, if the session is persisting there, it won't ask you to log in again. It won't ask you to do information about, give you information about the username and IP, everything. So because it's either stored in the cookies, and cookies are stored in the load balancer persistent storage layer here, or it can be stored as just a session in the load balancer itself. So there are different ways how a session is maintained, and this session information will be used. And there can be TTL associated when the session need to be terminated, or if it is idle for certain time or certain days. So these sticky sessions are also possible with the load balancer, perhaps possible with the reverse proxy as well, if there is a persistency persistence attached with the reverse proxy, if those are powerful enough. And then it helps in horizontal scaling, that as we discussed. So it ensures the, because of the load balancer is taking care of systems which are down, which are expanding, which are shrinking, which is completely invisible to the end user. The client is not able to see that. Load balancer is abstracting everything. So it is allowing the horizontal scaling of the backend system and separation of web layer from the application layer. So this is how we, as we discuss. So load balancer here is isolating any changes to the backend system, the application layer or the persistence layer, to the end user. The client doesn't see what's going on. Client doesn't see how many servers are up, how many servers are down, or are we expanding, or are we adding more servers here. All this abstracted and load balancer is taking care. So all this abstraction is load balancer is allowing, which is allowing our backend servers to horizontally scale or shrink or fall and or fail over to another server in case of the one server is down. So all these capabilities are allowed only because load balancer is here and taking care of this abstraction. So this is very high level, the load balancer and its advantages. Now next we go into the layer 4 load balancer, lower 7 load balancer, to see how exactly the routing works, and then routing algorithms. Before going into that, I would like to take any questions you have in high level about the load balancer before really dive into the algorithms of particular load balancer techniques. Yeah, please go ahead.
Hi, Shailaja. I do have a question. So you mentioned that it is not exclusive that the load balancer can fail itself. Can you talk a little bit about what strategies are available to take care of the load balancer when failing? How can we recover, maybe?
So are you asking about when the load balancer itself is failing? Am I right?
Exactly. Yeah.
Okay. Yeah. So if you attended my previous sessions, we discussed about high availability. Same techniques are applicable for the load balancer as well. So load balancer also can be a distributed system internally. While for simplicity, we are simply saying that this is a one centralized service, but internally load balancer itself can be a distributed system internally. So similar to how you design a backend service, in the load balancer, you probably can have multiple servers acting like together like a load balancer. And for the end user, this looks like a simple load balancer exposing a range of IPs here. Let's say it's just exposing 5 IPs here, but internally it could be a together of multiple back servers internally. So if one server is down, obviously our high availability sessions, as we discussed about, other servers keeps taking the request. This is one option, one approach. And then we do have active passive and active active. This one also we discussed in the previous sessions. So we do have a replica of the same one. This is the primary, let's assume. Oops. We have the replica of the same one, which is active. It can be active passive. In case of active passive, it doesn't take requests. It will simply keep taking the replica of the incoming information here and keep storing it. When this server is completely down, that's when the passive becomes active. It will keep, as long as in a passive mode, it silently sits there. It keeps taking, monitoring the primary, replicating its primary information to this secondary, and keeps it there silently sitting. When primary is down, that means again the same technique here. It keeps checking the heartbeat of the primary. When the heartbeat is not received within a couple of seconds, usually within milliseconds and not even seconds, then it immediately starts taking the request and it becomes active. Other option is active-active. In case of active-active, the requests are distributed. So let's say for IP ranges from 10 to 20 are going to the this primary one. The IP ranges from 20 to 30 going to this primary 2. So those are distributing the load. Both are active, both are distributing the load. If this one failed, then this one takes the additional load. So the one, if you remember, we discussed consistency hashing last chapter, sorry, in the last session. At that time, we discussed how consistency hashing can be used to distribute the data across multiple databases. The same technique can be used to distribute the load as well. For example, for a range of requests are going to primary 1, another range of requests going to primary 2, and another range of requests going to primary 3. Then when one fails, that extra load is taken care by the additional extra active servers here. So a load balancer also is like a distributed scalable system internally. Just that instead of taking the data, instead of serving the data, it is doing a different job. It is serving the load. That's the only difference. But overall, anything, once you understand that's the reason I covered previous sessions, active, passive, high availability and distributed data partitioning, because those concepts are the same in any higher end distributed system. You know, whether is it networking or data distribution, or it could be load balancing, is the same. So internally, while it's a simply small diagram load balancer here to make it simple for you to understand, internally it's a distributed, highly scalable system, just that it is serving the load, not the data.
Understood. Okay, thank you.
Are there any more questions?
I don't know. I was off for a bit, but I can see that you've already spoken about sticky sessions, which is great, because one of the things while choosing load balancer is your use case, and whether, you know, most importantly, because of the nature of your use cases, whether it's sticky sessions are if it supports sticky sessions, you want to choose that load balancer. So I just wanted to highlight that.
If you have any questions, do speak, because I struggle a little to read the messages faster. If you speak, it becomes more easier for me to answer. Yeah. So now we know why we need a load balancer. There are different techniques how load balancer is distributing the incoming request to the backend servers. The first option is layer 4 versus layer 7. Layer 4, if you see the networking model, the OSI model, layer 4 is the network translation layer, that is at the IP address value level, IP address range. Layer 7 is at the application layer. That means it understands for which request, what is the request path, what is the request header message, and what is the request format, etc. So it really intercepts the incoming message and understands what it is. Whereas in case of network, it doesn't really look into the message in the packet. If you see, just assume a network packet here, the IP address and the port, which is at the visible to at the network translation layer, whereas the actual message, what is the request? For example, get google.com so and so, add the header information, go get this one, or the message format, type, protocol, everything. This extra information, which is at the application layer. So the translation layer, the layer 4, only looks at the IP address and port and the protocol information, not everything else. Only based on this, it makes a routing strategies or routing choice. And the reason why we usually go for the layer 4 is quite faster, because it doesn't really need to go and look into the message. It doesn't need to really decrypt the message. The message which is encrypted, which is inside the pocket as encrypted, it doesn't have to decrypt. So in this case, it doesn't have to decrypt this message. There is no need to do the SSL termination unless there is we configured it to do so. It doesn't need to do SSL termination. Just looking at the IP information, it can make a decision. So it is usually faster. So and another reason is usually I'll come to that a little later. Otherwise, it's confusing. So let's assume I'm getting an incoming request and I'm looking at the something like hash function of the source IP and port number, destination IP and port number and protocol. Using this only, I'm making the routing strategy. Here is the incoming request. I'm looking at what is the source IP. For example, the request based on the source IP, if the request is coming from the US, I will send the request to the server which is located in the US. And otherwise, if the request is coming from UK, I will send the request to the server which is located in the UK. So that is based on the IP. You are making the geo strategy. The other one is the port. For example, if the port is 123, that means my service running at the port 123, which is a billing service. I'm sending the request to the billing service. If the port is 567, then okay, someone is asking me to get the photo. Okay, I'll go and get the photo. I will send it to the photo service. So only looking at the source and destination IP and port, the routing is happening. Let's assume we are developing a Google photo service. Let's assume. So when there are two kinds of requests we can get. One is get me a photo. That is a photo service, need to take care of that. Second one is buy a subscription. In case of that, the request has to go to the billing service. What I can do, I can run my photo service instances on the port number 567 in the backend. Doesn't matter about the destination IP, because here we are not looking into destination IP. Whereas the billing service is running at the port number 123. Let's assume so. Okay. Now, so this one is running at the port number 123. This one is running at the port number 567. Here we are abstracting. There can be multiple instances of billing service. Need not be just one. Let's assume it can be 10 billing services and 5 photo services. Let's assume so. Let's assume this IP address is 10. This IP address is let's say 20. So what happens when there is incoming request here? The load balancer, it looks into the IP value. It continues the same TCP connection. It doesn't change the connection, the same TCP connection. And in the TCP pocket, usually when the incoming request, let's say load balancer's IP address is, let's assume 30. Usually there is a format for the IP, but I'm making it simple just by using simple numbers. And so the external word only sees the load balancer IP values, not the back end IP values. So the incoming request, when the pocket comes here, it contains the IP number of the load balancer 30 and the port number 123. So the client understands that this is a billing request and sends the 123 here. The client sending here, for example, Google Photos app, that sends that this is a photo request. So I'm sending the port number 567 here, or it could be in the header or somewhere in the metadata. Then the load balancer here looks into 30. It says that, okay, I need to send you to billing service, takes the IP address of the 10, updates the destination IP from 30 to 10, sends a request to the billing service, takes the response back. So there are multiple mechanisms here. Some load balancers can be configured to get the response to them and from there send back to the client, or they can let the backend system directly send the response back to the client. So in case if the response need to come back to the load balancer, then here the source IP also will be updated to the load balancer IP. In that case, the backend system, when it is serving the request, it sees that, okay, I need to send the response, and what was the source IP, looks at 30, sends back to the load balancer. Otherwise, if this is not configured, then it sends the response back to the end user directly. So there are load balancers where you can configure. Do you want this response to go through the load balancer or directly from the backend system to the end user? So this is how the layer 4 load balancer works in high level, where it's just looking into the IP and port and protocol information only. It is looking into making the decision based on that. Whereas in case of layer 7 load balancer, here if you see, it looks into the incoming pocket. There are multiple ways how it does in the layer 4. One is the path based. For example, if it is a REST API, let's assume if it is a typical normal API, it can go to normal API service. If it is admin, it can go into the admin services. Or if it is a static, okay, the static content is served by the CDN, then go send it to CDN. This is one example. There are different approaches, and there can be a combination of this as well. For example, if the domain is photo.example.com, then go to photo service. If it is payment.example.com, go to payment service. Similarly, header based, where in the header we say that what are we trying to do, where are we coming from. Similarly, content based. So because the layer 4 can decrypt the message and look into the actual content, it can see, okay, the request is coming for subscription, then go send it to a billing service. Similarly, cookie based, we're looking to the cookie. Okay, this is beta testing end user, so go send it to the latest version of the servers. Otherwise, looking to the session ID and send the corresponding session info, going on in that backend server. So on. So overall, there are different mechanisms, but all of them, if you see, this is going and decrypting the actual message, looking into the information. Maybe for some of the approaches may not really doesn't need to decrypt as well. It can just look into the header which is visible, and then make the routing decision. So that is the difference between layer 4 and layer 7. But there are some advantages with the layer 7 which are not existing in the layer 4, because layer 7 is really looking into the actual pocket. You can do the smart routing, whatever kind of routing you wanted to do, because you really have access to the actual pocket. So there's a reason you can do whatever smart routing you wanted to do. For example, if the incoming request is a JSON, based on corresponding particular JSON fields, you can do some special logic of the routing that can also you can do. And also, because it is looking into the actual pocket, it can detect, we can scan for the SQL injection or malware, any security vulnerabilities in the incoming pocket. That can also be done in the layer 7, which cannot be done in layer 4, because in the layer 4, we really don't look into the pocket. And also the SSL TLS termination. Ideally, the TLS is above the layer 4. So if theoretically speaking, only layer 7 should be able to do the TLS termination. But this kind of distinction is not so easy in the real practical systems. Yeah, so this is the layer 7. Now, before going into the routing algorithms that we have, I would like to take any questions do you have on the layer 4 versus layer 7? Yeah, please go ahead. Amrita Singh. Your voice is not so, I can't hear you well. Can you be a bit louder? I can hear very little. Yeah, please go ahead. Uh,
Yeah, Amita, we can't hear you. Maybe you need to be closer to the mic, or I don't know what's going on.
in case
very
if you are
faint.
in case you can send a message in the chat, that's also fine. I can read it into it.
slightly better, but faint.
Sorry, it's not clear to me. Can you send me a message?
We can move on to Irene meanwhile.
Okay. Yeah, go ahead, please. Irene, please go ahead. Are you able to hear me, Irene? We're waiting for you.
Okay. I don't know what's happening with Irene, but Amita has asked her question. So we'll, yeah, if you can read out her question aloud and answer. Thank you.
Yeah. So, Amita, question, yes, is very good question. In case the internet services call each other, would LB come into the picture? Yes. Actually, the image we are showing here is very, very abstracted. There are load balances all over internally in the enterprises, not just in one place. Here, we are just showing the importance of why we need one from coming from the client. But actually, if you take in this example, here, if you see the service, photo service is coming, which is sending the request to the backend databases. And there, for example, if there are only, let's assume 3 photo services instances running, but actual database data is distributed across many shards, let's assume. In this case, there can be one more load balancer here to do the distribution of the incoming request to the database read request. The databases to read the data from databases, to write the data to databases, so on. So there can be load balancers internal as well, can be spread across organization in various places, not only in the database persistence layer. It could be there. For example, in this example, if you take the billing service, is for simplicity, the billing service probably having multiple instances running in the backend. Then probably you can have one more load balancer here to actually send a request to the one of the instances. While primary load balancer is taking care to distinguish between which kind of service the request is going to. Once it is hitting the billing service is still probably having a load balancer to hit the actual instance. There can be another load balancer, the smaller mini one, to hit the persistence layer here. So in an organization, in the practical terms, in an organization, there will be load balancers in different places. May not be as powerful as the actual main load balancers, which is taking care of the requests coming across different geolocations, but the smaller load balancers do the distribution of the requests into the backend, whereas the backend systems. They may not be looking into the security as well, because the security part is already taken care. Those are internal into the systems, so probably they don't need to do the SSL termination as well. They're simply doing the caching and the load distribution. So yes, really in practical terms, in bigger organizations, load balancers are there in multiple places within internal to the system, which are not exposed to the end user. Did I answer your question? Thank you. Yeah, Irene. Sorry, Irene. Please go ahead.
Apologies, I died, had to get back on. I don't know if you've maybe answered it with your last answer. What I was going to ask was, you went through layer 4 and then layer 7, and when you were describing layer 7, the fact that you can do that extra check for security vulnerabilities, and in particular SQL injection, then in my head I was thinking, well, why would you ever do layer 4? Because surely a company would want to do it right at the first point of contact, really, before passing it on through their systems. But then you suggested in your answer to Mita that you have smaller load balancers doing different things. So I think my question really, I can sum it up by saying, would you ever do layer 4 at the first load balancer in your
So yes, in a layer 4 can be actually, in real practical terms, there can be multiple types of load balances can be used in different places. So if first, in this case, in simple example here, if you are just using a simple one layer 4, and in this case, if you are not checking for the inside the message for the vulnerabilities, then that responsibility goes to the backend systems. The backend systems have to do that. So when load balancer is not doing some work, the extra work is going to the backend systems. But in ideal practical, in bigger organizations, layer 4, for example, can be used simply to do the geo routing. For example, when the request is coming, should the request go to the US or should the request go to UK? This kind of routing can be done by the first level of the load balancers, which is just the layer 4. But then the second layer of the layer 4 can be at the layer 7 and and doing the actual higher levels of the job, like SSL termination, and then looking into the vulnerabilities, etc. So the first layer could be a simpler one to simply in a very high faster manner to send a request into different geolocations, and then within the geolocation there can be a higher end load balancer to do the actual decryption and the SSL vulnerabilities. In case by any chance if it is not happening, and if our system is small, simple enough to not have any load balancer, in that case, that kind of work probably have to be done in the backend server. So somewhere we have to definitely look for the security vulnerabilities, either it's in the backend or in the load balancer level.
Yeah, thank you. But you would do it if you've got load balancers. You would definitely do it before it hit any of your services at the back end.
That's ideal situation to be.
Okay.
Yes, ideally.
Okay.
Yeah.
Thank you. Thanks for confirming. Thanks.
Yeah, even when the lower 7 is very good in doing all these jobs, still lower 4 is useful because it is very fast. Main difference is if I show here in this case, same TCP connection is continuing from the client to the backend, whereas in case of the layer 7, the TCP connection ends here. The TCP connection. So the TCP connection is ending here, the load balancer level. Here, load balancer is having its own connections to the actual backend services. So it's not as, and also it's looking into the actual message. So it's not as fast as the layer 4. So layer 4 can be useful in very high level where we need to do the very quick routing based on the location, and there are higher end load balancers there. Or in internal systems, where in the lower 4 internal systems, we are no longer worrying about the SSL termination, no longer worrying about the vulnerabilities. These are already taking care of the upper layers even before requests coming to this load balancer. Even those cases also, a layer 4 load balancer is useful. For example, when you are sending your request from your billing service to the backend, the database layer, at that time you don't need to worry about the vulnerabilities and the SSL termination, because that is already done by the one load balancer before. In that case, you just need one fast load balancer to distribute the request. In that case, you can go for the layer 4 load balancer. Yeah, go ahead, please.
So Shailaja, I just wanted to, based on these questions that came, so the layer 4 is the transport layer, and that, like you said, is very high level. So there's no access to the, no detailed access other than, okay, this is the IP, some of the like very high level. There's no translation, there's no decryption happening at that layer. So any load balancing, like you said, is based on location, like IP-based routing. Okay, this IP is from here, so let's send it to, I don't know, America, which is the closest. And then if you go down to the application layer, that's when the in that layer there is, like we really have access to, this is the request, right? Because this is where you said the SSL termination has happened, some encryption, decryption has happened. So you have more access to, this is the request, this is the payload, and you could have some rules to then further do more specific routing. I just
Yeah.
wanted to just confirm that that's this is the understanding.
That's correct. That's you're very right, actually. So it's like the layer 4 is just looking at the very high level information like IP address of the source and destination, the port numbers. Doesn't really look into the actual message, doesn't really snip and see what is there inside the message. So that's the reason it's faster, because it's just passing the same TCP connection without really terminating the connection, without really decrypting the actual message, and without really doing any additional logic, just looking at the already available values in a network pocket directly. Whereas the application layer, the layer 7, is really doing more. It's decrypting the actual message, looking into the message values based on how we configure the logic, where we tell the load balancer which fields to look into, which values to look into, and what to do with that. So it's doing more logic. So it's not as fast as the layer 4, but it is more powerful because it is giving more freedom to you to do how to do the load balancing and your own smart logic, and also it's doing a lot more functionality. It's allowing you to do a lot more functionality, like looking into the vulnerabilities and avoid a lot of work for the backend servers by doing many of the things at its own layer, at the load balancer layer itself.
Thank you.
Yeah, Irene, you have more questions, I think.
Yeah, just clarification as well. You mentioned in layer 4 that it appeared that the load balancer would change the IP address going forward. So the IP that the external client accesses is then mapped to the internal IPs and back. Is that right? Just wanting to confirm that.
Yeah, that's correct. So there are, again, this is not a universally doing logic, but different load balancers, even at the layer 4, are giving you options to do differently. So there are options like the incoming request, the layer here in the layer 4, the incoming request, load balancer can simply decide which backend system to go and simply send the request to the backend, and backend can directly respond back to the client. This is one way. The other option is load balancer takes the request. It doesn't really terminate the connection. It just simply overrides the destination IP with the billing service IP and sends the request. And while coming back, it can directly send it to the client. The other option is not only the destination IP, it can also override the source IP so that the response comes back to the load balancer. The backend system does the work, sends the response back to the load balancer because the source IP is the load balancer IP. And load balancer can do its own logic if needed and send the response back to the end client. But this is all happening in the single TCP connection. So the connection is the only one. It is not terminated. Whereas in case of actually there are some layer 4 load balancers which allow you to terminate the connection as well. There is a lot of flexibility there, but in high level, that's how the situation is. But in the layer 7, the connection is terminated here. So the client can keep waiting for the update here, response here. But the load balancer uses its own special connections into the internal environment, does the job, take the response, send the back to the client in its in the same connection, or other asynchronous methods that we discuss in a while. So this is how the difference between layer 4 and layer 7. Is that clear?
Thank you. Are there any, do we call these specific terms, or is it just different algorithms? Strategies that used, is there a term to refer to these as, if we were to look them up?
There are no particular naming as such other than the layer 4, layer 7.
Okay.
But yeah, but even at the layer 4, there usually some services allow you optionally choose what to do, in what manner you want it to do. So yeah, that's the reason if you see some of the articles, they say that this layer 4, layer 7 naming is not so correct, because there are some services called layer 4, but still they go and look into headers as well and other protocol information as well. There are some layer 7 services which probably still do some of the work that layer 4 is doing. So it's not so easy to distinguish. There is, but this is the theoretically, for our understanding, this is how these are organized. But in practical systems, These are like mixed up together. Many things are mixed up together. Did I answer your question?
Yes, fully. Thank you. Thanks.
Now we are done with layer 4, layer 7. Now we discuss about the different topic routing algorithms. So even after layer 4 and layer 7, still we need to do more algorithms. For example, if you see the billing service here, this billing service probably having multiple services, multiple instances in the backend. So when you're saying when your system is too big, there are so many incoming requests, even for the billing service, let's assume, then you need to send a request to one of the instances of the billing service. So in that case, there are multiple algorithms. You can choose the one which is right for your system. Random, which is just choose one of the randomly choose one of the backend instances. For example, billing service is having 10 instances, as let's assume. You can just randomly choose one out of them. This is not a very ideal strategy because it is always possible to send too many requests to the same instance and overloading the same instance. So it's not an ideal algorithm. Then least busy. In the least busy, how to define a server as busy? Is it based on the amount of load, how much CPU memory and how much load that particular server is taking? Or is it based on the number of ongoing requests? So let's assume if it is based on the load, the backend instances always need to keep informing the load balancer periodically what is the current load they are running. For example, there are 10, let's assume there are 10 backend instances, then load balancers need to be informed about load. And this need not be always accurate because the load can be suddenly spiked up within a few microseconds and nanoseconds as well. So what the load balancer probably having periodic information about the load going on each and every server, but it may not be always accurate. So decision based on the least load may not always be accurate for a small time span. Now, if we are going for the other option where the least number of ongoing requests, for example, you can say this one is having currently 3 requests, this is having 2, this is having 1, then it will probably go to the least number of requests on the server with the number of requests, ongoing requests as 1. But in this case, this is also not an ideal algorithm for all the situations. For example, if single request is too huge and involving a lot of work in the back end, compared to 3 requests here, which are very small and not so demanding requests. In this case, this system probably is not so busy compared to this one. But for different applications, different algorithms are more suitable. So for depending on your system, whichever is good for you, you can choose that one. In case of system design interviews, you can simply go for the one of these. You can simply say, I will go for the least load or least ongoing request. These are good enough for most of the systems. Otherwise, option is a session based. For some of the system designs, you need to go for session based because you need to give a better end user experience. For example, if anything need to be done persistence in the session, for example, if you say, let me take one example. One of the session, the best option for the session. Yeah, let's assume ChatGPT. You're chatting with the ChatGPT. You gave ChatGPT about your current resume and asking it to update your resume to suitable for a leadership role. Let's just take an example. You did upload the resume. ChatGPT is having your session information. Suddenly, your laptop crashed, or you logged off, or you went out for any reason, and your session information has gone away. Then when you come back again, you need to start everything from the beginning. So that's not a great end user experience, and it wastes your time as well. So for those kind of systems where session based is more important, the load balancer can maintain your session information on particular there are multiple places where the session information can be maintained. Either this load balancer itself can maintain in a persistent database somewhere here attached to it, or it can say that, okay, this backend system is going to have session information about users 1 to 10. This backend system is going to have users information about 20 to 30, so on. So when a user request comes, it checks. First time it chooses one of the instance, stores the session information on the backend system. When the next time the same user comes, it has to send the request to the same backend system. So your session information can be retrieved without spoiling the end user experience. So in that case, what we usually do, we take the user ID or the session ID and we hash it and we choose what is the backend system corresponding to that. The other option is a round robin. Round robin is suitable when you don't really need a session information. For example, you're just going in this order 1, 2, 3, 4, and so again 5, 6, 7, 8, so on. So in these cases, round robin is suitable. For example, if you're just paying subscription of Google Photos once in a year, let's assume. Once in a year, when you're paying for subscription, you don't really need to maintain the session. The incoming request can be sent to one backend. You make the payment, you are done. Next time, next year when you're paying again, it can go to another backend. You can make the payment. In this case, there is no persistence required, and round robin is suitable, good enough. So these are different routing algorithms. There are many more as well. Consistent hashing is also one of the routing algorithms here, possible routing algorithms here. Yeah, so I'm done with the routing algorithms. Now, with this one, we'll be done with the load balancer. So let me just finish this quickly. Coming to the cons, the disadvantages, the main problem is because this is the centralized load balancer itself is sitting as centralized system between the client and backend. It can become a performance bottleneck if there are too many requests for the load balancer itself to handle. If the load balancer is not powerful enough to handle all the incoming requests, and it can become too busy and it can become a bottleneck there. So that's the reason usually load balancers are nowadays a combination of both hardware and software, using very powerful hardware to do most of the work at the network, low-level network layer. So this may not be a real problem in nowadays if you are having enough money to go for a higher end load balancer. And then again, single point of failure. So see, as I mentioned, while load balancer is solving the single point of failure of the backend systems, but it itself can act like become a single point of failure because it is sitting in between the client and the backend. And if it dies, then we won't be able to take any incoming requests. So that's the reason the load balancer, the higher end load balancers are usually distributed, highly scalable systems, internally using high availability mechanisms that we discussed in the last sessions, like active, passive, replication, redundancy, everything. So this is so this is another one. But when the moment you go for higher end active, passive kind of systems, the configuration becomes more complex because when you say load balancer, you're not dealing with a one system, you're dealing with a set of servers acting like a distributed system together. So it's going to be more complex to manage as well. Yeah, these are the disadvantages. Now I will take questions on the load balancer if you have any, and if you don't have any, then I will go for next one, load balancer versus reverse proxy. Going to go for which one in a real systems? Are there any questions? If you're not having any questions, I'm going for the next section. So now load balancer versus reverse proxy. When to use which one? This is a theoretical explanation, but nowadays it's more difficult to make a choice because now many systems are acting like both nowadays. So reverse proxy is ideal for small setups where we probably have only one backend system, backend server, or only one or two backend systems categorized by the kind of work those are doing. Or else for the internal setups where we don't really have a lot of load. We don't need to distribute the load probably, but we just need something for security purpose or monitoring purpose or to control the access, authorization, authentication, or rate limiting. For those kind of simple cases, probably we need a reverse proxy. The other option is, yeah, when you need one of the features of the reverse proxy, like SSL termination, caching, compression, decryption, everything, security anonymization, where we don't want to expose the backend IP addresses at all. Those kind of places, you need a reverse proxy. So ideally, when you are in a startup mode, we probably go with the reverse proxy. But nowadays, you're having many open source load balancers, which are free as well. So probably you can just go with the load balancers, even if you're in a startup mode. So that's also there is more choice nowadays. Now the load balancers, in theoretically, when do we want to go? When you are having multiple servers and need to distribute requests, and when you need when you need to support high availability in your backend systems. So whatever we discussed in the last previous sessions, when we want to have high availability, horizontal scaling, when we need that ability to do everything in the backend without spoiling the end user experience, without letting the end user to notice whatever is going in the backend, that's when you need the load balancer as the abstraction. So here are some of the open source options: Nginx and HX proxy. Sorry, this is HA proxy, my mistake. So both of them work as both reverse proxy and load balancer. Both are open source, both are free. So because nowadays you're having these free options, I think most probably you can just go with the load balancer with all the features of the reverse proxy enabled. Now coming back to the response. Yeah, so now if you see, there is one difference. When the request is coming from the client, going to the load balancer and going to the backend system, the backend system sending the response back, it is sending the response to the load balancer. Now load balancer is sending the request back to the client. So there are different mechanisms here. In case if the request is processed synchronously, the load balancer can just send the response back to the client in the same active connection. So if you see, request is coming from the client, going to the load balancer, going to the service, response is coming back to the load balancer. This connection is still active in case of the synchronous request. If it is not timed out, then load balancer sends the response back to the client. Whereas in case of asynchronous, for example, if there are Kafka messages involved here, if the Kafka queuing is involved, or any kind of asynchronous work is involved here, asynchronous means doesn't need to take hours, but even if it is taking few seconds, usually the client connection may time out if it is more than few milliseconds. So in those cases, we can go for asynchronous response. Client sends a request, say for example, create resource. Load balancer takes a request, and then backend system says okay. It just says okay, doesn't say done, and sends a request ID to the client. Client can poll for the response, keep polling for the response. So this is another option is polling for asynchronous response. The other option is the webhooks and WebSockets for asynchronous response, where client doesn't have to really poll, doesn't have to wait for the response. Instead, the backend system, when it is done, it can directly send the response back to the webhook or WebSocket. So we will have a separate session on WebSocket and webhooks because it is in our latest topic. It requires a session on its own. We will have a separate session on this one. Yeah, with this, today's session is done. Sorry for going over time.
No worries, Shailaja. One quick thing. I just wanted to say, in our organization, we use it's a platform. We build a platform similar to if hosting our services, and we have on the front we have load balancers, and then the load balancers then send the traffic to the gateway, right? API gateway, and the API gateway uses the reverse proxy, which then uses Kubernetes cluster load balancing for the pod. So that's how our setup is, and we use the of the reverse proxy. So all I'm trying to say is sometimes you could, depending on the systems and what systems give, you could use this and the load balancers, the gateway, and the reverse proxy as well. For it all to work. And it's again like whole system design, how you design the system, and you can design the systems depending on the tech solutions you use. I don't know if you've covered gateway at all, but I just wanted, if you could just share, because we've covered reverse proxy, and load balancers. Another aspect related to this system design is also gateway. And if you wanted to speak a few words, and if, the team, it'll be great for them to know what a gateway is in context of all of this.
I can just explain a little in theoretically, but is it okay if we are out of time?
Can everyone give the thumbs up if you want to know very briefly what a gateway is? Yeah, okay, Irene says yes, because it's a very important concept in the same realm. Thank you, Omar. Okay,
So gateway. So gateway is more like translating the incoming request to another set of incoming requests. For example, if you take, I'll just give one example. Let's assume you are having AWS cloud. When you're sending request to the cloud, you're sending API, you're invoking API of the cloud. Then what does AWS cloud do? It takes the API and it checks to which service the request has to go to. For example, the request is going for the DynamoDB, then it will convert that incoming API into the corresponding DynamoDB API. Or if the request is coming for the S3, it will convert the API to corresponding S3 API. So it's like it is more, it's not really at the load balancing layer. It's nothing to do with the load balancing, to be honest there. It's not the networking as well. It's about more about the application translating one incoming API to one form to the another form. And again, it's similar to the reverse proxy. It's at a centralized place, so it can do more work than just doing the API translation. It can do the authentication. For example, when AWS Cloud first gets the request, it does the authentication and it evaluates what these user capabilities are. For example, like generating a token with what are all these users the user is capable of doing. So user can access the DynamoDB, user can access the S3, user cannot access HDFS on AWS, for example, because they never bought the subscription HDFS, for example. So this kind of token information, when it does the authorization, it generates. Along with the request, it sends this token information to the downstreams. For example, it sends a request to DynamoDB, and DynamoDB runs it as its own service. It looks into the token. Okay, what is this user is allowed to access? Okay, this user is allowed to access DynamoDB. Okay, I will let this user to access this one. Okay, this user is allowed to access this particular table. Okay, I will let this user to access that, so and so. So it is doing API translation as well as authorization as well. So other than that, I'm not sure what else other capabilities it can do, but it is more towards the application oriented. So if it is AWS cloud, its responsibility is different. If it is Microsoft Azure cloud, its responsibility is very different. So the one centralized place is taking incoming requests, doing some actions, and converting it into the internal different APIs internally. If you can actually, Rajni, if you can explain how are you using gateway in your system, probably that will be more practical example compared to the theoretical example I'm giving.
Yeah. So basically, reverse proxy, like you said, the solution. I'll start with reverse proxy at the back, right? So we have Kubernetes applications. Kubernetes has its own internal cluster. It also gives you external load balancers, but we don't use it. So it has its own internal cluster load balancers for the pods. So multiple pods. So when a request hits a Kubernetes, service that we have implemented, then multiple pods, it does its internal routing to the pods. So think of microservices implemented using Kubernetes. Then we have the reverse proxy that sits, that connects to these Kubernetes cluster. And this reverse proxy does a lot more like the transformations, right, that we need for the request response. And it also makes sure that keeps the internal network. So we have an interface to our internal network because we have multiple. It's a very complex system. So we have a reverse proxy that sits, that knows what sort of transforms it needs to do, So we can handle geography, region, etc, etc. Then we have an API gateway, because at the end of it, our system exposes APIs that will be used by the UI and other services to actually use the system. This system will create instances for you, like startup, like say, oh, I want this service, then it literally creates one service, automatically sets it up and creates the service for you. So the gateway is like the API service that your request comes in. So say for example, I want to create an instance of this. I want to do XYZ API, actions REST API, and that's what the gateway does. So it's like a centralized way for handling all the requests and what to do with it, which means authentication, authorization, all of it is back in here. Rate limiting is also in here. And the rate limiting like literally sits between like the gateway. It uses the reverse proxy and gateway and works with it. Then we have the load balancers at the front, where the external request hits our organization. So that we use front door in Azure to basically take all those requests, and we do a little bit of routing there, like you said, geography based routing based on headers. So it's a system because of our use case. This is the best system to give us the flexibility we need. And interestingly, I think we've used everything in bits and bobs, like load balancers, API gateway, reverse proxy, and Kubernetes having its own load balancer.
Yeah, so see, now we think that women coding community is a volunteering system, how complex the internal maintenance is. So definitely we need to appreciate the leaders of women coding community for maintaining these systems. I'm sure it's really demanding work for them to maintain this.
Yeah, I can't agree more. It is a hideously complex system, but required.
Yeah, so I actually so my presentation today is mostly theoretical because I didn't really dig my hands into load balancer before. But once we are done with a decent number of system design sessions, if we have time, we can probably have a walkthrough into some of the open source load balancer like Nginx to really see how internets are working. Or else, if anyone is having hands-on, if we can volunteer to give one session on that, that would be really great.
I have worked a lot with load balancing, so I'm happy, Shailaja. I could.
Oh, I'll be super happy. You should have told me that upfront. I would have handed over to you.
Oh no, it's okay. I'm very happy that you're doing this. I can only interject, and I'm helping. I'm only the co-host here. I'm just trying to make sure that the listeners here get the most of you, may make the most of you. You're incredible, and the knowledge that you have is incredible, and I want that to reach all our audiences who are at different levels, right? So it's all about that. Thank you so much, everyone, and if you can give a round of applause to Shailaja for these are all like when you use it, you will understand a bit more. But to even explain this in such level in such a short session, Shailaja, it's really wonderful, and for me it was like a great refresher as well. So thank you very much, and thank you everyone who turned up. And if you want, if you want us to give feedback of how we want to run it, feedback for Shailaja, feedback for any topics you want to cover, how we want to run it, please let us know and we'll make it happen, because we want these sessions to really help everyone. So thank you, Shailaja. Amazing session. I really can't say how grateful and thankful we are that you are here today, and giving your piece of knowledge and sharing your piece of knowledge and taking the time, your own personal time, to make this happen. And I know the preparation of the slides and everything, that is a lot of work behind the scenes, and I understand how much you would have worked hard to make this session possible. So thank you, everyone. Have a lovely Sunday, everyone, and then we will catch you up in the next system design session by Shailaja. Take care. Bye. Bye.